Good afternoon. So I don't know how many of you have seen the message that I put there. Early next week, most probably Tuesday or Wednesday, you're going to have a quiz. That will be quiz 4, and that's the last quiz for the semester. So that way, the physics course, we have ensured that you're going to really get time to prepare. So for last minute, having components and evaluations, we want to avoid it at all costs. So next week, we'll finish quiz 4, and with that, we are done. After that, it's just a matter of few more classes. We'll finish the syllabus. After that, start preparing for your MSEM. Okay, I hope that's clear. So now let's continue with the syllabus. As mentioned in the last class, there are many ways by which you can change the magnetic flux. After all, you know that when you have a loop and when you change the magnetic flux through the loop, within the area of the loop, then there is an induced EMF and an induced current to oppose the change in flux. Okay, so what are the ways by which you can change the magnetic flux has been dealt with here. You either change the magnetic field, or you change the area, change the direction between the magnetic field and the area, or change the area of the magnetic field which is exposed to the loop. So like this, there are various ways by which you can change the flux and thereby induce the currents. So now today we're going to see one of the applications of this. This is going to be called the motional EMF. This is a very important part of the syllabus. Please listen. It's called motional EMF. So look at the right hand side on the figure here. You have a square or a rectangular region of length B where the magnetic field is uniform, and the magnetic field is denoted by the cross, which means the magnetic field is into the plane of the screen. Okay, and you can see here one rectangular loop. You're seeing a rectangular loop, and you can see that a part of the loop, a length x of the loop, look at this, a length x of the loop a length x of the loop is in the magnetic field, and the rest of it is outside the magnetic field. Okay, and let d be this dimension. D is the width of this rectangular loop. There is no source of EMF, no current. Okay, now what happens is a person from outside, a person is trying to pull this loop out. A person is trying to pull the loop out. So now look at this. Only at this instant of time, okay, only this much area of the loop is exposed to the magnetic field. Whatever is outside that area is not exposed to the magnetic field. I hope this part is clear. Okay, so now what we intend to do is by applying a force, you're going to apply a force. You can see here a man is applying a force and then trying to pull this loop out with a velocity v. With a velocity v, he's going to pull the loop out. So when he pulls the loop out, what happens to the area exposed to the magnetic field? What happens to the area of the loop exposed to the magnetic field? Anyone? First of all, what is the area exposed to the magnetic field? I said D is the width and X is the region inside the magnetic field. So you can see that dx is the area of the loop exposed to the magnetic field. I hope that part is clear. Next, what we'll do is let us find out what is the flux through this area. Only in this area magnetic field is there. So let's find out what is the flux. Let us assume that B and area vector are parallel to each other. So you take the area vector also parallel to B. Okay, so that would mean that flux is equal to integral B dot dA simply becomes B into A. It simply becomes B into A. Okay, because they are parallel and B is uniform, it becomes B into A. Okay, so what is our A? What is our area? A is area you already got is B into X. So we can say that the flux is B into D into X. Are you following the step, guys? Yes or no?
Yes, ma'am.
Yeah. So the flux is B into A, which is B dx. So this is the flux through the area of the loop exposed to the magnetic field. So now let the man start pulling it. He's pulling it in this direction by applying a force. And let us say that he's pulling it with a force so that the velocity is a constant. Now, some of you who know mechanics will wonder, how can you apply a force and have a constant velocity? Because whenever you apply a force, F is equal to m into a, there should be an acceleration. But I'm saying he's applying a force to counteract another force that is going to be discussed in a few minutes. So what happens is he has to apply this force and make this frame move with a velocity v. Okay, when it is moving with a velocity v, you can see that x becomes a function of time. You can see that x becomes a function of time. X is decreasing or increasing as a function of time. X is increasing or decreasing as a function of time when this man is pulling it out?
Decreasing.
Decreasing as a function of time. It is decreasing as a function of time. Thereby, what he is actually doing is he's trying to change the flux by changing the area exposed to the magnetic flux. He's changing the area. So let us say that induced EMF is d phi by dt, you know. First, let us not put Lenz's law. Let us directly just get the modulus. So modulus of phi b is b capital D x by dt. B and capital D are constants. The width is a constant, magnetic field applies a constant. It doesn't change with time. Only x is changing with time. So what will you get? I can write one more step. B into D into dx by dt. What is dx by dt? What is dx by dt? Dx by dt is velocity. Dx by dt is simply the velocity. Okay, therefore, you can see that the induced EMF is given by BdV. Induced EMF is equal to BdV. So what is happening here? Because of a motion of a loop in the magnetic field, you are changing the magnetic flux, thereby creating an induced EMF and thereby an induced current. Now, because it is happening because of the relative motion between a region of magnetic field and a loop, this kind of an induced EMF is called motional EMF. This kind of an induced EMF is called motional EMF. I hope this point is clear. There's nothing new you are doing. We just discussed some 4 or 5 methods of changing the flux and creating a field. So this is creating an induced EMF. So this is one. By actually moving, you are changing the area exposed to the flux, to the field, or thereby changing the flux, thereby there is an induced EMF. So this method of creating an EMF is called the motional EMF. And this EMF produced is called the motional EMF. Okay, now let us say, so you got the expression for the motional EMF, it is BdV. Okay, now let us see what is going to be the current. What is the induced current? From Ohm's law, you know that current is equal to EMF divided by R. If R is the radius, if R is the resistance of this loop, it's after all a metallic loop, so resistance of the loop is R. We know induced EMF is BdV, so BdV by R is going to be the current induced. That's going to be the current induced. So now let us apply Lenz's law. So you are seeing that the flux is decreasing as a function of time. If flux is decreasing as a function of time, the induced current will set up a magnetic field in the same direction as the field. In the same direction as the field. Therefore, you're going to see that the current that is applied is like this, okay, as given in the figure, and it is going to create an induced magnetic field in the same direction as the applied magnetic field. Okay. Next. Okay, so this is what you're seeing. The induced current is in the clockwise direction and thereby opposes the change in the flux, a reduction in the flux. Now let us discuss the force. We talked about a force that was actually pulling. Okay, so let us now start naming these forces. First of all, let us take the 4 arms of this rectangle and call this force as F4. Okay, or let me call this as F. So there is a force F1. Let us say there is a force F1, there is a force F2, there is a force F3 on the 3 arms. Okay, and what are these 3 forces due to? What are F1, F2, and F3 due to? These are because of current carrying conductor in a uniform magnetic field. You know that whenever a current carrying conductor is in a uniform field, it will experience a force F is equal to IL cross B. IL cross B. Therefore, you are going to get some forces. Let us try to see what these forces are going to be. If L is, so we said this is D, right? We said this is D. Therefore, I have to make a small change here. By force of habit, sometimes, we write certain things. So this is not L, this is D. Okay. So the force on this part, force on this part, okay, force on this arm, let's call it as F1, and let us try to get the direction of F1. Use your right hand rule, IL cross B. So when you do that, you are seeing that your thumb is in this direction. Thumb is in this direction. So that means there is a force F1 on this part of the arm. Okay, now let us look at F2 and F3. You can see that the length exposed to the magnetic field is X in both the cases, but the currents are in opposite direction. The currents are in opposite direction. Therefore, the forces also will be in opposite direction, and these two forces will cancel out each other. Okay, therefore, you will get F2 plus F3 equal to 0. Okay, now let us come to the opposite side, this side. On this side, there will be no magnetic force. There will be no magnetic force on that arm simply because that arm is not exposed to magnetic field. But this arm is exposed to an external force applied by the man. This arm is exposed to an external, it's not exposed to magnetic field, it's exposed to an external field, mechanical force exerted by the man. And look at the direction. He is applying it in this direction, whereas F1 is in the opposite direction. And I told you something. I said that he will apply a force F so that the loop moves with a constant velocity. So that the loop moves with a constant velocity. What does that mean? That would mean that to move with a constant speed, the external force that force that an external agent applies must be equal and opposite to F1. The force that he applies will be equal and opposite to F1. Therefore, we can say that F that he is applying is equal to minus F1. Is this point clear, guys? Okay, so now let's look at, so there is a force operating and it is moving an object with a speed v, with a velocity v. So immediately you can talk about what is the power expended. What is the power spent by the external agent to do this? So look at this. Here we are calling this force also, or I will do one thing. I should actually put a minus here. I should actually put a minus here because F1 is in this direction and this F is equal to minus F1. Okay, so I may put a minus here to say that the external force, this is external force, and we are parallel to each other. External force we already found out. External force we already found out is IdB. It's already IdB. Therefore, the product of these two will be IdBV. IdBV. And since we are just talking only about magnitude, I'm dropping this minus, okay, but I just explained that minus so that you will understand why that F1 dot V, we have written it this way. Because F external is equal to minus F1, okay? And then you are after all getting what is the power. So you can simply do the dot product and forget the sign. You can write IBDV, okay? And now already you got an expression here for one part. What was that? IDDB. Okay, so what we will do here is, okay, you're going to get this ultimately as D square B square V square by R. Can someone explain how this step came? Anyone? Look at this. I, you got it as BdV by R. In the previous page, you got I is equal to BdV by R. So we're just making that substitution here. So we're just going to use that here. So ultimately, you got an expression for the power expended. So that is the rate at which the external agent is doing work and putting energy into the system. Because he's doing work, he's doing positive work on the system and pulling the loop. So what is happening to that energy? So energy has gone into the system. So there is a rate at which energy has gone into the system. So what happens to that energy? That energy is lost as Joule heating. That energy is lost as Joule heating. You people in your plus 2 have studied power is equal to I square R. Power is equal to I square R. Okay, so that is the rate at which energy is lost from the wires whenever there is a current flowing. And this kind of a power loss is called Joule heating. It happens because of the heating of the wire. So P is equal to I square R. So once more substitute for I, and then you're seeing that these two fellows will match. These two fellows will match. That means the rate at which energy is dissipated as heat is the rate at which that external agent is doing work on the system. External agent is a mechanical fellow. He is doing mechanical work on the system, but then the energy lost is in the form of heat energy. Okay, and in the process, what is happening? In the process, there is a induced current set up in the loop. Now, this is called motional EMF, and this current is called motional current. Okay, so now you've understood that there is going to be Joule heating. Okay, now, what is the implication of that? Let us see. Now we are going to introduce you to a term called eddy currents. We are going to introduce you to a term called eddy currents. So we have seen that whenever magnetic flux changes through a loop, there will be a current produced. So instead of a loop, what if I have a metallic disc instead of a loop? I had a loop and I was pulling it out, a wire loop. Instead, if I have a metallic disc and then pull that disc out, again, the magnetic field through the region of this metallic loop is changing. Okay, so now metallic disc is changing. So what happens in this case is loop will be formed. Loops will be formed. A loop need not be formed. You need not have a wire for a loop of current to be formed. Even within this metal itself, you will find loops of current set up like this. You will find loops of current set up like this. And why is this loop set up? These loops of current starts getting set up in the metal because the magnetic flux through the metallic piece is changing. Okay, now these kind of currents are called eddy currents. These are called eddy currents. So if somebody asks you what's an eddy current, you have to just say that when the magnetic flux through a large piece of conducting metal changes, then there will be current loops appearing in the metal. Now these currents are called eddy currents. And please remember, wherever there's an eddy current, there is going to be heat because of Joule heating. Okay, so this eddy current can be a disadvantage in certain situations, because eddy current is going to produce heat and therefore it is going to increase the internal energy. It will heat the material and that's not something that you want. So what should you do to avoid heating, or how do you prevent this? Eddy currents cannot be changed. Eddy currents will be there whenever you're changing the magnetic flux. But how do you avoid this Joule heating and loss of energy? So for that, what you have to do is you have to laminate the material. Laminate the material exposed to magnetic field. What is the meaning of lamination? I'll just explain. There is a figure which I have shown in the last class of a transformer. Okay. I'm sure you people have, how many of you have seen a transformer, a tiny transformer at home? Anyone? Have you seen, what I mean is, have you seen something like this? Okay, here you will see some wires and two part of the wire will be jutting out. This time, this side also, and this entire thing will be covered, so you won't be able to see these wires. And this part, you will actually, it's actually a ferromagnetic core. It's a ferromagnetic core. Okay, and if you see how this core looks, you will find that this is actually made up of sheets. It's made up of sheets separated from each other by insulation materials. So this entire thickness, how do I show that? Okay, so let's say this is a sheet. How you will see it is, you will see that this is, let us say, the body of the ferromagnetic core. You will see that this is not one single body. It's actually made up of a number of metallic sheets separated from each other by insulating material. Now, after I have said this, have any of you seen a transformer? Shit, this use and throw is reducing your exposure to a lot of things. If I had asked this question 3-4 years back, I had at least a few students in the class who have said, yes ma'am, we have seen this transformer. There's nobody who has seen this transformer. A tiny piece, yeah, it was just a tiny piece like this, okay, the thick metal in the form of a rectangular O, and then you see one bundle of wire coming this side and this side. Have you seen this? Nobody's seen this? At least say yes or no.
No, ma'am.
No. Okay, you just, I don't know, yeah, how you people have not seen all this. I have had students, in fact, I have seen it. We have all handled these, some appliance at home, gets damaged, this transformer piece will be there, your fan and all will have it. So what happens is, the electrician will leave it behind and we used to play with it. Okay, so the core should actually, so how you will understand what is this core. You can see there is a solenoid on the left and on the solenoid on the right. These solenoids are actually to produce magnetic field. If you put a ferromagnetic material inside, the magnetic field will increase. So this core is basically for that only, and core will be normally made up of a metal and a ferromagnetic metal. Okay, so what happens is, when there is a current change, look at the primary circuit is going to go on keep changing direction. It's an AC current. So what will happen when it changes direction, then obviously the flux is going to change. When the magnetic field is changing, flux is going to change. Flux is changing means there is going to be an eddy current. Eddy current means heat. Okay, a lot of heat will be there because the frequency of changing direction will be very high. So to avoid that, it will not be made up of one single metal. It will be actually a number of sheets which are stuck together by some kind of insulating epoxy, some kind of a gum. Okay, now this process is called a lamination. By doing that, you're not going to prevent eddy. Eddy will be there, eddy loops will be there. But what happens is, you are not giving a big piece of, you're not showing a big piece of material for the magnetic field. Instead, you are showing tiny pieces of metal. So when you're showing tiny slits of metal, what happens is, let's say this is a piece. If it was not laminated, the eddy current loop would have been like this. Eddy current loop would have been like this. And there is another expression for power loss. One is I square R, which we saw. The other one is EMF square by R. This comes from Ohm's law. V by I is R after all. Okay, so this is another expression. So what happens is, what will be R here? R will be the resistance of the eddy loop. Resistance of eddy loop. Okay, now in the second case, let's say you're doing the lamination. In the second case, you are doing the lamination. Lamination means it is not one single metal. It is made up of a number of thin pieces of metal which are separated from each other by lamination. So now in the second case, what happens is, when you're going to expose it to a magnetic field, there will be loops formed, but the loops will be like this. Eddy loops will be formed. Eddy loops will be formed like this throughout the metal. Okay, many loops will be there. And what happens is, because many loops are going to be formed, this EMF is going to be the same, but R increases tremendously. R increases tremendously because the length of the current loop effectively increases by many times. Instead of one single loop, it's going to be many tiny, many long loops. Okay, so what happens is the effective length of the current loop increases or R increases. Because R increases, EMF square by R becomes smaller. Therefore, the resistive heating or the effect, one of the negative effect of eddy currents is that heat. So that can be avoided by doing this lamination. Is this understood? Okay, so it's not as if eddy currents are really all the time bad. There are some situations where eddy currents can be positive, like in the case of your induction stove. Induction stoves came more recently for cooking your food and all that. Okay, but before that, induction furnaces were normally used whenever you wanted to heat something to high temperature without actually exposing it to air. There are some materials, which you want to heat, but the minute you put it in air and heat it, it gets oxidized. You don't want that to happen. So what is done is it will be put in tiny capsules. It will be sealed in tiny capsules and then put in a magnetic field. And this magnetic field will keep changing quickly. When the magnetic field changes quickly, what happens is there will be eddy currents form and these eddy currents will heat this material. Okay, so this is the principle of an induction furnace. But of course, now induction furnaces are no longer, they are still in use, but then they have come home. They have come home and you have your induction cooking stove. So there also what happens is you're going to have an AC current. Okay, AC current is a current that is going to keep changing direction. If I say that the AC current has a frequency 60, that means 60 times it will keep changing direction per second. And every time the current is changing, magnetic field direction is changing. Every time magnetic field direction is changing means the flux is changing. Okay, so by using a current, AC current, which is going to change the magnetic field direction rapidly, you're going to put a material which can be affected by the changing flux. Only such materials can be put. You can't put all materials on an induction stove and cook. So what happens is there will be eddy loops formed and it will heat the material and cooking takes place. Okay, so this is how eddy currents can be used for induction stoves. Then another place where you can use eddy currents will be in magnetic braking. Please remember one thing, in all your mechanical brakes, what happens is there is a bush and then it sits on something and then rubs against it. By friction, you're actually stopping the motion of a vehicle, let us say. A disc brake. Okay, so what happens in some situations is if the speed is very large, when this friction comes into picture, what happens is there is a lot of heat and the resultant wear and tear that is happening. Okay, you don't want that to happen. Next thing is when there is a mechanical braking, what happens is the braking distance also tremendously increases. Trains, for example, when you're trying a braking, what happens is the driver sees a cow on the rail, passing on the rail, but then when he stops it, it takes 1 or 2 kilometers for him to actually stop the train when it is in full speed. Okay, so the braking distance is also large. So two negatives. One is the heat resultant wear and tear, and the second is the braking distance. Of course, third, there is also sound. So you said, now how do you avoid all these things? This is where your magnetic braking comes into effect. So what happens is you've seen when you were trying to pull the loop out of the magnetic field, there was a force trying to resist that. So there was a force trying to resist it. That's exactly what you're going to do. The wheel is put in a magnetic field and then the magnetic field is changed. So what happens is there is a resistance to the movement, which is your braking. And it will be very efficient at high speeds because the magnetic force increases with speed. F is equal to QB cross B. So magnetic forces increase tremendously with velocity. Okay, therefore, this will be most efficient at high speeds. Plus, there is no wear and tear, no sound, and the braking distance is also short because it's very efficient. So with this, I have discussed eddy currents, two advantages and one disadvantage and how to overcome the disadvantage. Okay, now let's go to, if I ask you in this class, how do you produce electric field? All of you would tell me that if you have a charge, all around it, there is going to be electric field. Charge is a source, a static charge is a source of electric field. Yes, fine. But then today we're going to see that there is going to be one more source for electric field. That is going to be a changing magnetic field. If you change a magnetic field with time, then what you get is an electric field. And the electric field that you're going to get, we just now, till now we talked about induced EMF induced current. Next, you're going to see that there is an induced electric field. Before we get there, let me give you a definition for EMF. Let me give you a definition for EMF, electromotive force. EMF is defined as the work done in moving one unit of charge around a closed path. You know what is work done? Work done is integral F dot ds. And if I'm talking about a closed path, okay, fine. Then what is F? F, you know, is Q E dot ds. Okay, but then I'm talking about 1 unit charge, 1 unit charge. Therefore, it becomes integral E dot ds for the closed loop. Now, the work done for doing this is called your EMF. This is the definition of EMF. Okay, with this definition, let's move ahead. Please, what I'm going to discuss now is slightly complicated conceptually, so please listen. So I don't know how much you are able to really see. Okay, there is a region. This is actually, let us consider a circular region. Circular region of radius r, having a uniform magnetic field into the plane of the screen. Okay. Now, in this region, let us put a wire, a circular loop of radius small r. Let us put a circular loop of radius small r less than capital R. And then let us change the magnetic field. And let's say we are going to increase the magnetic field. If you see the magnetic field is inside, area vector is inside, and then we are going to increase the magnetic field. So when you increase the magnetic field, that increase is not liked by your loop. So what happens? It wants to create a magnetic field in the opposite direction. Therefore, EMF and current will be as given in the picture. Okay. So this is induced EMF and this is current. So what is the meaning of current? Current means in that wire, charges are moving. That means in that wire, the charges are moving. Okay, now the question is, you all know from electrostatics that F is equal to Q into E. F is equal to Q into E. Okay, so when I say that there is an EMF, I am also talking about an electric field parallelly. I'm talking about an electric field which is driving the charges, which is making the charges move. Okay, for a moment, let us assume the charge is positive. So we are assuming that the electric field is moving the charges around in this circle. Okay, now the question is, and what does this EMF produce? EMF is equal to minus d phi by dt. That comes from Lenz's law. Okay, now what we'll do is, let us just, so we are saying that a charge will move only if there is a field. Charge will move only if there is an electric field. There should be a force and there is an electric field. F is equal to Q into U, so there should be an electric field. So now we have to see, electric field doesn't require any space. You all know that. Okay, so what we'll do is, will this happen? Will this electric field be there even in the absence of that wire? Let us remove that circular loop. Okay, let us remove that circular loop. This wire, you just remove. Okay, and put a charge at this location. Put a charge at this location and change the magnetic field. So then what is noticed is that this charge starts moving in a circle. The charge starts moving in a circle. So what does that mean? It means that there is a tangential electric field at all those points and it is driving this charge. Okay, so from this experiment, you can prove that there is an electric field. And what created that electric field? The charge didn't create the electric field. The charge didn't create the electric field. The charge is experiencing that electric field and coming around in a circle. So what created that electric field? The electric field was created by the changing magnetic field. Or for the first time, we are seeing a relationship between magnetic field and electric field. A varying magnetic field can create an electric field. Okay, so this is the connection between. So now we have slowly moved from statics to dynamics. We talked about magnetostatic till now. Okay, now we are moving from magnetostatic to magnetodynamics. Magnetic field is changing. So changing magnetic field can create or induce an electric field. So that's what we have seen. Okay, next. Just now we have seen the definition of EMF. So let's use the definition of EMF. Now what we are going to do is, let us now put a circular loop. Let us put a circular loop of radius capital R. Let us put a circular loop of capital radius R, capital R. Then what will be the EMF in that loop? Let us say what is going to be the EMF in that loop. EMF is E into, we have seen it is E dot ds. So for the circular loop, it just becomes E into 2 pi R, 2 pi capital R. Okay, so EMF is equal to E into 2 pi R. That is by the definition of EMF. Or simply we can write it as integral E dot ds. So this is the work done in moving a charge. Okay, so now what we'll do, so okay, this is the work done in moving a unit charge. In moving a unit charge. But then what is the work done in moving a charge Q naught? If you put a charge Q naught, what will be the work done? Work done will be E into Q naught, EMF into Q naught. That will be the work done. Okay, so now what you have to do is, you can just EMF is equal to minus d phi by dt, just write it in the form of electric field. So integral E dot ds is equal to minus d phi b by dt. Okay, so this equation is going to be one of the Maxwell's equations. And it says that changing magnetic field can produce an electric field. It can induce an electric field. Okay, and what is the direction of this electric field? The electric field has got the direction of the induced EMF. Okay, and the direction is given by the Lenz's law. Therefore, that minus sign comes. Okay, now the question is, I have a circular region. I have a circular region of radius R. Radius R, and there is magnetic field only in this radius R. Okay, now we put a loop on this radius capital R, and then we found there is an electric field. Is there an electric field inside also? Is there an electric field inside also? So what we'll do is, let us take a distance R less than capital R and do the same thing. Okay, let us take a distance small r less than capital R and do the same thing. So integral E dot ds is equal to minus d phi b by dt. Okay, so that's going to be E into 2 pi r. 2 pi small r, because small r is the radius of this loop. And what happens on the right hand side? Right hand side is minus d phi b by dt. That is going to be d by dt of b into a. A is a constant, so db by dt into a. What is a? A is the area of this loop, area enclosed by this loop. You are interested in finding the electric field here. Okay, therefore it becomes minus dB by dt into pi small r square. I'm interested in finding out what is the electric field at that location. What is the electric field here? So keep E on one side, take everything else on the right hand side, and I am interested only in getting the magnitude. Therefore, E is equal to half dB by dt into R, taking everything else on this side. Half dB by dt into R, or you're seeing that the electric field is proportional to small r. Electric field is proportional to small r for region small r less than capital R. That means the electric field will be zero bang at the center. For all other points, the electric field will be forming closed loops. Closed loops. Till now, you've seen that electric field will start on a positive charge, end on a negative charge. But here, for the first time, you're seeing this electric field will form closed loops like magnetic field. Okay. Now the next question is, okay, there is magnetic field in this region, capital R, but will there be an electric field at a point outside? There is no magnetic flux there. Will there be an electric field is the next question. For that, what we'll do is, let us take a region, capital R and small r greater than capital R. Then find out what is the flux. Please remember, flux is only in that capital R region. So it is B into pi r square. So now write the left hand side, E dot ds. E dot ds is E into 2 pi r. What is 2 pi r? 2 pi r is this. This is your 2 pi r. And on the right hand side, you are having, take this, differentiate, you're going to have minus dB by dt into pi capital R square. Listen guys, it is capital R square because the entire flux is enclosed by your loop. So it is pi capital R square. Now again get your E. E will be half dB by dt into capital R square by R. Or you're seeing that the electric field falls off with distance. After this capital R, beyond capital R, the electric field will be there, but it will fall off with distance. But inside, it is directly proportional to distance. Okay, and this electric field forms closed loop. So if I am going to plot, I will get within the circle where there is magnetic field, the electric field is linearly changing with distance. Once you reach capital R, so let this be capital R. Once you reach capital R, you're crossing it, it falls off as 1 by R. Here it is proportional to R. Okay. The next thing is, okay, here you can see, I don't know whether you're able to see, I have shown a loop 1, a loop 2, a loop 3, and a loop 4. Okay, now the question is, you are talking of EMF, all right, you are talking of electric field, all right. Okay, now what will be the induced EMF? You talked about electric field all over, but what will be the induced EMF in these small loops? Why should the loops be circled? If I take a small loop and put it the way I have here, then what will be the induced EMF will be the question. Now look at this carefully. In paths 1 and 2 are completely in the magnetic field. They're completely in the magnetic field and the change in the magnetic field. Therefore, they will have the same EMF. They will have the same EMF. Now come to path 3. Where is path 3? Path 3 is here. It is partially inside the field and partially outside. Therefore, in this case, flux is not the same. Therefore, EMF will be smaller. Now let us go to path 4. In path 4, what happens is electric field is there, but no flux is there. No magnetic field is there, so no magnetic flux. Therefore, though there is an electric field in that small loop 4, there will be no EMF. There is no EMF. Now we have come to the last slide. So now to conclude what we have studied in this last 10 minutes, I can say that there are two sources for electric field. One is charge that you studied in chapter 26. The other one is varying magnetic field, which you just studied. Now, you know that even from today's class, you've seen that if you put a charge in the electric field, it will experience a force QE. That will happen with both the fields. It can happen in electrostatic field and it can happen in this field also. Then, the field due to static charges start on a positive charge, end on a negative charge. They don't form closed loops. But electric fields due to the varying magnetic fields, just now we have seen, they form closed loops. They form closed loops. Okay? Next. You have seen in chapter 26 that these fields are conservative fields. Electric field there is conservative field. Conservative means work done in moving the charge through a round trip is 0. Integral E dot ds is 0. Okay, and you've seen that whenever you have a field which is conservative, then immediately you could write E is equal to minus del V. Or you wrote it as minus dV by dr or dV by dl. Your capacitor, everywhere we use this. We could write an electric field in terms of a potential. This you could do only because it was a conservative field. But come here. Here, integral E dot ds is clearly not equal to 0 because that is EMF. Charge into integral E dot ds is work done. That is EMF you see. Therefore, it is not a conservative field. Electric field due to changing magnetic field is non-conservative field and therefore it cannot be represented by a potential. You cannot talk about a potential. That's the reason why when we're talking of potential, we clearly say electrostatic potential. Electrostatic, to clearly say that we are talking about that field. A potential of that kind is not possible here. Then let us see this picture here. Here you see there is a collection of some charges. Come here. Some collection of charges are there. Let us put a wire around this and then connect it to a voltmeter. Connect it to a voltmeter. Okay. You are going to see a potential difference between these two ends of the wire. Because there is a field. The field is created by these point charges. There is a potential difference between the two ends of the wire. But then this potential, this voltmeter is connecting it and making it a closed loop. Okay, therefore what happens is, because it's going to be a closed loop, you register V equal to 0. You will register V equal to 0. Whereas here, let us have a solenoid. Let's have a solenoid through which you're going to pass current. Put the solenoid here. So when the current is changing, there is going to be an electric field. Okay, now in this region, if you put this kind of a loop, and you have seen that outside the loop also there is electric field. You've seen, no? So outside that solenoid also there is electric field, though there is no magnetic field. So here, if you put a closed circuit, you will find that integral E dot ds for the closed loop is not equal to 0. Therefore, there is a reading. There is a reading that you will register. Okay, so one could ask questions of this kind on the difference of the electric field due to these two varying sources. Okay, so with this, we are winding up the chapter. Anything you want to ask? What is that? Here you put a closed circuit. What? Somebody has asked something. You put a closed. What? Somebody has asked me. Oh, whatever I'm saying is appearing there. Shit. Okay. Okay. Yeah, anything?